So first, let me define what is MEMS for your audience.
Okay.
MEMS stands for micro electromechanical systems. It is taking really large things, miniaturizing them using semiconductor processing techniques. But the difficulty is this: even the most complex semiconductor chip has active and passive devices like transistors, diodes, capacitors, resistors. MEMS not only has that, but it has actually dynamic devices, physically moving devices, sensing devices. It's very complex. And so we licensed a technology, a concept for a quartz rate gyroscope using monocrystalline piezoelectric electric quartz, the material that is used in quartz crystals in your watches. Now, the concept of using a tuning fork to detect angular rate is not new. Sperry had already done that with the gyrotron in the very early 1900s. That was a huge, massive item.
It's a big tuning fork to figure out the angular rotation.
That's exactly right.
Got it.
Through the Coriolis force. Now, so we started developing this technology because we saw that a whole new generation of technology was needed to address the aerospace and defense markets. And we started becoming very well known. And during this period of time, we developed some of the most advanced inertial systems and sensors you could think of. The world's first MEMS-based inertial measurement unit. And that using our tuning fork. Now here, I might add that it was right around the time when the Berlin Wall came down.
Mm.
And all companies across the United States and the rest of the world were paying the price for peace dividend. And in our case, this great technology of ours did a tremendous job in the aerospace and defense market, but had not yet penetrated any high level or high volume manufacturing, as is typical for aerospace and defense. To give you an example, the highest we had shipped for any program was 10,000 units a year.
Mm-hmm.
And each axis, row, pitch, or yaw, was roughly between $1,800 to $2,200.
Wow.
And a full system could go into a couple of $100,000, a full inertial measurement unit. So here we were sitting with a great technology, which nobody else in the world had. And our market was collapsing right in front of us for this very important division of ours. We had many other divisions, but this was the biggest.
Mm.
So here was a choice, stick your head in the sand and die, or really take some very bold actions. I was president and CEO, but at the same time, and Charles Crocker was I was the president and chief operating officer and the CTO, and Charles Crocker was the chairman and CEO. And we had to do some really big soul searching. After performing an extensive market survey, we identified a significant growth opportunity for an extremely low-cost, solid-state rate gyroscope for the automotive application, for stability control. Now, stability control systems, they measure the yaw rate. A yaw rate is the lateral movement of a car, which means the intent of the driver. The computer compares that output with the lateral movement of the car and decides if the car, even in the slightest manner, is not going to behave with the intent of the driver. It takes control of the front left and right brakes in order to prevent a fishtail or spin out and roll over. And this is particularly important when you're going on slippery roads or taking very acute turns. Now, we identified this market, something we had no experience in, because we came from the A&D background. And most of the engineers had grown up with me many years. I got them all together and said, we've taken a decision that our aerospace and defense market is going down. We're going to go after the automotive market for electronic stability control and rollover prevention. And here started the biggest challenge of my life. Some of the great engineers said, you are asking us to develop the same technology in a very simple form at a very low cost. And we have developed with you some of the greatest and the most advanced chips that the world has ever seen using this technology. I said, yes, that's exactly what I'm asking you to do. Well, isn't that humiliating? I said, on the contrary. If you're that proud of what we developed, and which we are, let's go apply for a Nobel Prize. That isn't going to save the company. And my friends, remember, anybody can design anything given sufficient time and resources. The automotive industry, you have to design to cost. You cannot add one more cent. It's a totally unforgiving market. There is no vendor loyalty. If a person has been providing them something for years and years, and you come up and provide the same thing, with better specifications for a cent less, you're gone. Well, several of them balked at it. Several agreed, okay, let's do it. And I said, look, I'm giving you one more chance. I will have each and every one of you trained. We will bring in the best experts on handling quartz. We'll bring them from Seiko. We'll bring them from all the world's greatest places that handle quartz. We'll get the best quality assurance people from the automotive industry. We will look at our whole re-engineering of the company. I will personally lead that. Some agreed and others didn't. For those that didn't, and these were very, very important scientists and technologists I had to tell them that just the way an individual outgrows a company, sometimes a company outgrows an individual. I had to let them go. And the rest, I instilled a whole re-engineering of the company. I had to re-engineer the company without abandoning the aerospace and defense business. So while we were doing the aerospace and defense company, I had to overhaul and re-engineer the whole quality system, enterprise resource planning computer system, electronic data inter-exchange, customer ordering, statistical process controls, factory automation, technology road mapping techniques for continuous cost reduction, engineering design and validation techniques for lowest unit cost, and development of a complete global supplier base.
Ooh.
The biggest challenge, however, was changing the engineering mentality. As I said, designing to lowest cost versus just designing. The challenge was this, Andre, that we had to reduce the cost of our inertial sensors, which is called the quartz rate sensor. Eventually, it was named the gyrochip. From the $1,800 and $2,200 in access, 10,000 a year, to millions of units a month at $50 or less a unit.
Whoa.
You see the challenge?
Yes.
And the cost reduction occurred through selective investments in automation, significant advances in design techniques and mass production techniques. You can't just automate everything. Nobody has that kind of money. So to give you a background, the QRS, Quartz System manufacturing process and techniques were redesigned for mass production, primarily in fork fabrication, fork balancing, hermetic packaging, final assembly, calibration, and test. The labor-intensive process were replaced by automation and proofing against human error. Continuous cost reductions were planned with 5-year technology roadmaps. Products achieved the primary customer needs of performance and specifications and continuous fault detection capabilities for safety-critical applications. Established a common quartz fabrication facility that served both the aerospace and defense and the automotive markets. And these products, both automotive and aerospace and defense, took advantage of this single quartz rate fabrication facility where high volume automotive components were fed back into selected A&D products extremely favorable cost benefits. These major changes, based on leveraging the aerospace and defense technology into the automotive and transportation, and reverse leveraging the high volume, low cost automotive components back into aerospace and defense markets, allowed the company to dramatically ramp up production, shipping millions of units while it continued serving the aerospace and defense market.